Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 7, Coordinate Systems in 2- and 3-Dimensional Forms. Section 66, The Equation of a Conic. The results of Section 65 lead readily to the equation of a conic. By this is meant an equation in point, line, coordinates, which is satisfied by all the points, lines, of a conic, and by no others. To derive this equation, let A, B be two distinct points on a conic, and let equations 1, m equal to m1x1 plus m2x2 plus m3x3 equal to 0, n equal to n1x1 plus n2x2 plus n3x3 equal to 0, p equal to p1x1 plus p2x2 plus p3x3 equal to 0. Be the equations of the tangent at A, the tangent at B, and the line AB respectively. The conic is then generated as the point locus by two projective pencils of lines at A and B, in which MP at A are homologous with PN at B respectively. This projectivity between the pencils, equations 2, n plus lambda p equal to 0, p plus mu n equal to 0, is given, Theorem 6, Corollary 3, by a relation, equation 3, mu equal to k lambda, between the parameters mu lambda of the two pencils. To obtain the equation which is satisfied by all the points of intersection of pairs of homologous lines of these pencils, and by no others, we need simply eliminate mu and lambda between the last three relations. The result of this elimination is, equation 4, p squared minus kmn equal to 0, which is the equation required. By multiplying the coordinates of one of the lines by a constant, we may make k equal to 1. Conversely, it is obvious that the points which satisfy any equation of type 4 are the points of intersection of homologous lines in the pencils, 2, provided that mu is equal to k lambda. If m and p are fixed, the condition that the conic 4 shall pass through a point a1, a2, a3 is a linear equation in k, and hence we have Theorem 7. If m equals 0, n equals 0, and p equals 0 are the equations of two distinct tangents of a conic and the line joining their points of contact respectively, the point equation of the conic is of the form p squared minus kmn equal to 0. The coefficient k is determined by any third point on the conic. Conversely, the points which satisfy an equation of the above form constitute a conic of which m equals 0 and n equals 0 are tangent at points on p equal to 0. Corollary: by properly choosing the triangle of reference, the point equation of any conic may be put in the form x2 squared minus kx1 x3 equal to 0, where x1 equals 0, x3 equals 0 are two tangents, and x2 equals 0 is the line joining their points of contact. Theorem 7 prime. If A equals 0, B equals 0, C equals 0 are the equations of two distinct points of a conic and the intersection of the tangents at these points respectively, the line equation of the conic is of the form c squared minus kab equal to 0. The coefficient k is determined by any third line of the conic. Conversely, the lines which satisfy an equation of the above form constitute a conic of which a equals 0 and b equals 0 are points of contact of the tangents through c equal to 0. Corollary: by properly choosing the triangle of reference, the line equation of any conic may be put in the form u2 squared minus k u1 u3 equal to 0, where u1 equals 0, u3 equals 0 are 2 points, and u2 equals 0 is the intersection of the tangents at these points. It is clear that if we choose the point 1, 1, 1 on the conic, we have k equal to 1. Supposing the choice to have been thus made, we inquire regarding the condition that a line u1, u2, u3 be tangent to the conic x2 squared minus x1, x3 equal to 0. This condition is equivalent to the condition that the line whose equation u1, x1 plus u2, x2 plus u3, x3 is equal to 0 shall have one and only one point in common with the conic. Eliminating x3 between this equation and that of the conic, the points common to the line and the conic are determined by the equation u1 x1 squared plus u2 x1 x2 plus u3 x2 squared equal to 0. The roots of this equation are equal if and only if we have u2 squared minus 4 u1 u3 equal to 0. Since this is the line equation of all tangents to the conic, and since it is of the form given in Theorem 7' Corollary above, we have here a new proof of the fact that the tangents to a point conic form a line conic, chiefly Theorem 11 of Chapter 5. When the linear expressions for m and p are substituted in the equation p squared minus kmn equal to 0 of any conic, there results, when multiplied out, a homogeneous equation of the second degree in x1, x2, x3, which may be written in the form equation 1, a11 x1 squared plus a22 x2 squared plus a33 x3 squared plus 2a12 x1 x2 plus 2a13 x1 x3 plus 2a23 x2 x3 equal to 0. We have seen that the equation of every conic is of this form. We have not shown that every equation of this form represents a conic. See section 85 of chapter 9. Exercise. Show that the conic a11 x1 squared plus a22 x2 squared plus a33 x3 squared plus 2a12 x1 x2 plus 2a13 x1 x3 plus 2a23 x2 x3 is equal to 0 degenerates into distinct or coincident straight lines if and only if we have 3 by 3 determinant a11 a12 a13 a12 a22 a23 a13 a23 a33 equal to 0. Dualize. Assumptions A, E, P, and H0.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.